This example is going to look at a biology application of exponential functions. In particular, it's going to look at radioactive decay. So we're given the half-life of cobalt-60, which decays radioactively, and we're told that that half-life is 5.27 years. The idea of half-life is that we're going to consider that, or assume that cobalt-60 decays at a percent rate each year in this case. And what we'll know then is that after about 5.27 years, there will be 50% of the original amount left. So it doesn't matter how much we start with, we're always going to have half of what we started with left after that 5.27 year mark. So what we're going to look at here is modeling this with an exponential function. And this is telling us that if 15 grams are present now, we need to determine how many grams will be present in 10 years. So this will be a two-step problem. The first step is going to involve writing the formula for this function. And the half-life, so our general formula for something that with radioactive decay is that we have an output, n of t, and it will equal n naught, the naught being when t equals 0, so the original amount is what that n naught is going to represent, times e raised to the kt. So n naught would be that original amount, and then k is going to be that rate. Now, since it's decay, we're going to represent that decay rate with a negative, and k will be written in decimal form. So what we'll look at here is we first want to find k, and we will use the half-life to find k. We're given n naught, and so once we find k, we can input n naught and then find out how many grams will be present after 10 years. Okay, so first we're going to find k. Let's go through that. So the half-life tells us that we'll have 1/2 n naught. That'll be equal to that n of t when t is equal to 5.27. So we'll use this to set up an equation to solve for k. So what that will tell us then is that 1/2 n naught will equal n naught times e raised to the k times 5.27. Now, what we see then is that we have n naught on each side, so we can divide that out, and that will leave us then with 1/2 equal to e to the k times 5.27. Okay, so now to solve this, we have k in that exponent. We have an exponential expression with base e, so we'll use the natural log function to solve. So what happens then is that the natural log of 1/2 is then equal to k times 5.27. And so solving for k, we'll see that it's just the natural log of 1/2 over 5.27. And if we approximate k, we'll have to use a calculator to approximate that, but we'll see that it's approximately negative 0.1315. So as far as writing our formula, it's best if we use this exact value of k that we found. We'll have the least error if we do that. This approximate value is helpful, though, in that it tells us the rate at which cobalt-60 decays each year. So what this means then is that each the rate of decay of cobalt-60 is about, and so the negative, that's happening because it's decaying, but this 0.1315 is a decimal, and as a percentage, we'd write 13.15%. So the rate of decay of cobalt-60 is about 13.15%, and that needs a unit attached with it, which in this case is per year, coming from the fact that we used a year value for t. So our t in this case has to be in years. So now let's write our formula, and we'll see that we have n of t equal to 15, and then we'll have e to the kt, and this natural log 1/2 over 5.27 is what we use for k. It'll be a little difficult to write that, so I'll actually write it as 1 over 5.27. times the natural log of 1/2, just so it's clearer to write. And then that's all times t. All right, so as our last step, the question's asking us if 15 grams are present now, which is where that value of n naught came from, how many grams will be present in 10 years? So the only thing we have left to do is to evaluate this function when t equals 10. So we'll take n of 10, and all that we're going to do then is plug in 10 for t, so I'll have 15 e raised to this 1 over 5.27 times the natural log of 1/2 times 10. And when we put that expression into our calculator, we can approximate it, and we'll see that it's about 4.026. So our summary then, we'll answer this question. In 10 years, there will be about 4.026 grams. And we'll state in the sample.